Good evening, everybody. I'm John Hebber, Jr., Vice President of Geologist at Jackson Hole. Welcome here this evening. It's my great pleasure to introduce our speaker, Dr. Mark Clementz. And I'm particularly pleased to introduce him because he got his bachelor's in geology from the University of Missouri, Columbia. My alma mater. PhD in geology from the University of California, Santa Cruz, postdoc fellow at Smithsonian Institution's Marine Station in Fort Pierce, Colorado. He is research associate of the Smithsonian Institution, National Museum of Natural History, senior research fellow of the Alexander von Humboldt Foundation, and professor, not least, professor in the Department of Geology and Geophysics and program in ecology at the University of Wyoming. And there at the University of Wyoming, his paleoecological research focuses on the ecology of the past, and specifically the evolution of shallow marine coastal ecosystems. You say, what the hell does that have to do with Wyoming? Well, if you remember, and everybody who's come to our program should well remember, you go back 60 million years ago, and there was a hell of an ocean out here that went up through the center of North America and Wyoming. We are at sea level right here. So, through time and the role that vertebrates have played within these ecosystems. So if you would join me in welcoming Mark Clementz.
Cool, thank you. Can everybody hear me okay? Yeah. Okay. So when John invited me to come up here, I had already heard a lot about your organization and the talks that you guys have, because several of the faculty in my department have come up here before, and they've all raved about how wonderful the crowds are and the feedback that they get. So I jumped at the chance to come up here. So thank you for the invitation, and hopefully you enjoy the talk that I give today. So I'm going to, as John mentioned, I'm going to focus on looking at Wyoming ecosystems for the last 65 million years, but since most of you probably don't want to be here for 4 or 5 hours, I'm going to scale it back a little bit from what I had originally intended so that I can showcase some of the research that we've actually been doing in my lab. And we're going to focus on the early part of the Cenozoic, primarily the Paleocene and Eocene, so about 65, so right after the big extinction event, wipe out the dinosaurs, and then the diversification of mammals up into the end of the Eocene, so about 34 million years ago. So it's a big chunk of time, and it's a very interesting time. So this illustration here is representative of what conditions were like in Wyoming at that time. So think hot, humid, tropical, subtropical conditions. And I'm going to give you a little taste of what the mammals, the faunas, were like during that period. So now, one of the best things about living in Wyoming and working in Wyoming is that we have an amazing fossil record. And I know you guys have had several talks where you talked about the geology in general, but I'm going to focus on how that geology has really benefited paleontologists because we get such an amazing fossil record. So, after late Cretaceous, early Eocene with the Laramide orogeny, you have a lot of these basins that developed across the state. And the cool thing about those basins is that you can think of them as storage boxes or archives of past life over time. And the nice thing about some of these basins, particularly this one here, the Hanna Basin, is that they accumulated a lot of material in a very short amount of time. So one of the probably more famous formations to the north, the Hell Creek Formation up in Montana. This is sort of the time period of the earliest Paleocene, so around 65 million years ago, so right after the extinction event. It's got about 50, 60 meters of section preserved there. And then to the south, the Nacimiento Formation, a little bit bigger, about 80 meters. And then you go into Wyoming, particularly the Hanna Basin, and over that's pretty much that same time interval. So each of these PU1, PU2, PU3, these are land mammal ages. So they're ages defined by the mammals that you find in the rocks. So we can use them to kind of date the age of the sediments. So in the Hanna Basin, we have about 550 meters of material, so almost 10 times as much material. So you really have a long, drawn-out record, so high-resolution information that you can pull out of this. And so the cool thing about this is, with that record, my predecessor at University of Wyoming, Jay Lilligraven, was able to accumulate a lot of material. And it wasn't just Jay, there were several paleontologists before him. that developed the collections that we have at Wyoming. And now, for the size of our campus, we have an incredibly diverse and well-representative collection of Wyoming fossils. We have about 50,000 vertebrate fossil specimens and almost 100,000 invertebrate fossil specimens. And that doesn't even include what we have in our rock and mineral collection. So if you saw talks by Ron Frost or Art Snoke in the past, you know that they love to collect rocks. So we have tons of rocks from them as well. The nice thing about this section is that, as you can see here, this is a range chart showing similarities in fauna. So think of each of these little bars as a different species that you find within the record in those basins. And so there's a big difference between basins that are to the north. These are mostly up in Montana and northern Wyoming. And then these are basins to the south in Colorado and New Mexico. And so there's a big disconnect between the two. And then study of the basins or the fossils from the Hanna Basin has really filled out this record and showed that that location was pretty much where those different faunas overlap. So you get representation of both faunas from the north and faunas in the south in the Hanna Basin. And it's because we have so much material that you have really good coverage of all the mammals that are going to be found there. So thanks to the work of these earlier paleontologists, this accumulation, this amazing collection, a lot of the work that I do has been building off of that work. So collections are not, even though they're made up of dead organisms, they're not dead themselves in terms of how people use them. And so once fossils are collected, there's still a lot of research that we can pull out of them. And that's a lot of the work that I do, is focus on collections-based science. So for today's talk, I'm going to focus on sort of 3 sections. And the first section is going to be pretty quick. And it's just going to be a general overview on how environments and faunas changed over the Cenozoic, particularly focusing on that early part from about 65 to about 30 million years ago. And then I'm going to talk about the way that I've been using fossils to extract environmental information. And so this is where, instead of just using the fossils themselves, we focus on the chemical composition of the fossils to tell us something about what the plant life was like at the time, or what the temperature was like at the time. So I'll go with a little background into how we use fossils to do that. And then again, I've mentioned that I've restricted the talk down a little bit. So we're going to focus on primarily the Paleogene. So that's that interval right after the extinction to about 35 million years ago. So about a 30 million year window. And I'll focus on the early part of that period when mammals radiated after the big extinction of the dinosaurs. And then I'll move forward a little bit in time and focus on the Middle Eocene and talk about the development of what we call megafauna. So when the big mammals started to appear, because as I'll show you in a minute, there was a bit of a delay in going from the common body size of mammals during the Mesozoic, when dinosaurs were around, less than a kilogram, so smaller than a house cat, to what we see today, where you have elephants, or in the past with mammoths and big rhinos. So there was a big gap between, or jump in body size between those two extremes. So that's kind of where I'm going to be going for the talk. So to start with the overview, I need to give a little bit of a background in terms of the techniques that I'm going to be using. And so I mentioned the chemistry of the fossils, and specifically what I do is I focus on looking at the isotopic chemistry. So we look at particular elements, and then we focus on the abundance of different isotopes. And I'll explain how this relates to ecology or environment in a little bit. But I just wanted to kind of clarify that when I'm talking about isotopes, these are basically, atoms of an element that share the same number of protons and electrons, but differ in their number of neutrons. So what that means is, since protons and electrons are the same, chemically they behave the same. But since they have additional or fewer neutrons, that changes the mass of the isotope. And it's that mass difference, that slight difference in how much they weigh, that affects how they are passed on or fractionated within the environment. And I'll explain that a little bit further. And so the number values that you'll be seeing through the talk are going to be what we call delta values. So there'll be an isotopic value for a particular fossil specimen, and that will look at the ratio of isotope A to isotope B in the sample. And we normalize that to a standard because these differences are usually very, very small. And then we multiply that by 1,000 in order to make it a little easier to work with. And the units that we use are per mil. So they're similar to parts per thousand, but it's not quite the same because everything's normalized to a standard. Okay? So I just wanted to kind of give this introduction because when we talk about climate in the past, one of the best records that we use is an oxygen isotope record. So paleoceanographers, these are people that go out and collect core from the oceans and analyze the sediments that they retrieve. These are some examples of these guys on one of these trips that they take out there. And mostly what they're focusing on, you have different people that specialize in different areas, but you have a lot of micropaleontologists that look at these little tiny fossils. These are forams. These are small little unicellular organisms that play a big role in marine ecosystems. And the part that we like is that these little unicellular organisms actually form calcified tests or shells, which this is an example of one here. And these bulbous ones that look like a bunch of balls that are stuck together, these are planktonic, so they're living up in the upper water column. And the nice thing about the shells that they make is that when you look at the isotopic composition, specifically the oxygen isotopes in the shell, the oxygen isotopes vary in relation to temperature. So we can measure the oxygen isotope values of these guys, which are really abundant in these sediments, and then generate a curve like this, which represents thousands and thousands and thousands of forams that have been analyzed on a mass spec. And we get isotopic values that we can then convert back to temperature. So for you guys, important thing to note is that when we look at oxygen isotope values, so they're going from -1 to 4, for oxygen isotopes, lower values tend to mean higher temperatures. Higher values, so positive values, tend to mean cooler temperatures. So if we look back in the past, here's the Cretaceous Tertiary boundary, so about 65 million years ago. Values are really high relative to today, and then they show this steep increase as you go into the Eocene, and particularly the early Eocene. And then, more importantly, one of the time periods that paleontologists and geologists have focused on is this spike, where you get this sudden rise, or actually it's a drop in oxygen isotope values, but a rise in temperature. That's called the Paleocene-Eocene thermal maximum. And it's this period of rapid climate change when temperatures rose 5 to 8 degrees C within a very short window of time. So geologically speaking, so we're talking about 10,000 years, something like that. And because of that, you get a lot of extinctions at that time period because there's such rapid climate change, a lot of animals can't adapt. And so that event had actually marked the boundary between these two time periods, the Paleocene and the Eocene. And it's only later that we realized that there was a climate event associated with it. We knew that the faunas changed, but we didn't know why. And so now with this record, where we can reconstruct temperature over time, we can see that after that event, temperatures declined, but then rose up to what we call the early Eocene climatic optimum, when temperatures were at their peak in the Eocene. And then after that point, there's this gradual decay in temperatures until you get to the Oligocene, when you get this start of ice formation in Antarctica. So temperatures have dropped significantly. It's thought that this is probably triggered by a big drop in global CO2 levels. And so once you start forming ice in Antarctica, we shift from being this really warm environment where we have tropical conditions, not just in Wyoming, but all the way up to the Arctic Circle. You have tropical plants that are present that far north. You have crocodiles up at 75 degrees north latitude. So really unusual conditions during that time. So we move out of this sort of what we call a greenhouse world into the start of this icehouse conditions where things get cooler, things get drier, and we get a nice record of that change in the oxygen isotope values of these little forams. So that sort of gives you an idea of how temperatures have shifted. So I'm going to focus on this early time period here, primarily because it's so unique, so different from what we experience today. Hopefully it'll spark your curiosity about what paleontologists can tell us about life in the past. Okay, so with that in mind, you have this big warming event that's going on early in Earth's history. when we look at the mammals, there's been a lot of work trying to look at how mammals responded to that big shift in climate, but also how they responded to the removal of dinosaurs from those ecosystems. And we know that mammals radiated. They diversified into a variety of new species, and this is an accumulation of number of species over time that was collected by John Alroy. And here we have the Mesozoic numbers, so small number, 20, 30 species at that time. And then after the extinction event, and note that there is a bit of a drop, so mammals were affected by the extinction event. It's just the mammals that we see today were the lucky ones that made it through, or at least their ancestors were the ones that made it through. And then right after that extinction event, you get this dramatic increase in the number of species. And then that increase continues and then kind of plateaus as we go through the rest of the Cenozoic. So that's sort of like the carrying capacity that most terrestrial ecosystems can attain, is this sort of upper level. At the same time that this radiation diversification of species is happening, you also have a big diversification of body size. So this graph is showing time on the x-axis again. Again, it's by John Alroy, who's very prolific in his publications. And he documented how body size has changed, and not just how big mammals got, but also the range of body sizes that we see. And what he found was that right after that extinction event, there's a little bit of delay, but then you get this big increase in body size. So this is in a log scale gram weight. So here where we have 1,000 grams, that's that 1 kilogram size. So that's sort of the upper limit for most of the Mesozoic when dinosaurs were present. And then after that, you see mammals get big very quickly. So you're getting up into 10 to the 6, that's getting close to a ton in body size. And then we're up to the 10 ton, which is close to the upper limit for mammals. The cool thing about this graph is that what he showed was that initially that range is completely filled by mammals. It's dark all the way across from low body size to upper body size. And one thing that we see in this diversification is that we kind of have a wall. Like this is the lower limit, how small a mammal can be. And we don't see mammals getting smaller than that. The only time period where we have mammals smaller than we do today is the Eocene. So generally there's this correlation between temperature and body size. Mammals tend to be bigger, cooler climates, smaller and warmer climates. So with the Paleocene, Eocene warm period, greenhouse conditions, mammals got smaller. So there's a tiny little mammal, and I forget if I believe it's a rodent, but don't hold me to that. But it's actually it's an insectivore. So it's like a little shrew, and it would fit on the eraser on your end of your pencil. So little tiny guy. So, and this fossil was found in the Bighorn Basin in Wyoming. So a lot of these big discoveries are found within our state. The other thing he noticed was that, we kind of get this upper level kind of plateau, but then this area opens up. So sort of this middle window, which was sort of the upper limit in the Mesozoic, becomes this sort of empty space where we don't have a lot of mammals. And the thought is that you get sort of set in a particular evolutionary path where either you stay small or within that small range, or you get big. And so you get this split within mammal groups sometime in the Eocene when we start developing modern faunas. So groups of mammals that are similar or ancestral to what we see today. So this is some of the early work. This was done in the late 90s. Since then, there was another team that focused on just looking at maximum body size. So how big, what are the biggest mammals at any given time? And so they did this back into the Mesozoic and showed that, during this time, mammals were still pretty small most of the period. So this is, again, a log scale. These are in kilograms, not grams. So this is looking at something like around 4 or 5 kilograms, sort of the biggest mammal that's present during that period. And then right after you get to the extinction, at the end of the Cretaceous, you get a jump in body size, and then there's this gradual rise and then a plateau. And it looks like, based on estimates looking at fossils, is that the largest mammals that we get are at about 15 to 20 tons. That's the biggest a mammal can be on land. We know that whales get bigger in the ocean, but that's about the largest that an animal with that physiology and ancestry can get. The cool thing about this study was that they looked at it from a global perspective. Then they also looked at it from across different continents, where you have different faunas over time, and they showed that all of them get close to this upper limit. They don't follow the same trajectory. Like in South America, it takes a little bit longer to get to their peak body sizes. But in Africa, Eurasia, North America, places where you get a lot of mixing in the faunas, because those continents were connected at different times in the Cenozoic, they all show the same upper level. So they all kind of get up to that 10 to 15 to 20 ton sort of range. And then the part that I'm interested in is that when you look at which groups filled that body size niche, which mammals got big. And early on, primarily for the time period that we're going to be talking about today, these are ancient groups of mammals that have no descendants today. So these are early experiments in big body size by different groups. And it's only later, as we get into the late Eocene, so around 40 million years ago, that we start seeing groups that we'd probably be more familiar with perissodactyls. These are odd-toed mammals like horses, rhinos, tapirs. Some of the biggest mammals in the around 30 million years ago, 25 million years ago, these guys were perissodactyls. They were big rhinos that got up to the 15 to 20 ton size. And then after that, from the Miocene on, this big body size niche has been filled by the elephants, by proboscideans. And so they've been consistently the large mammals on most continents, Eurasia, Africa, North America. It's always been elephants that have been the big guys. But for my talk today, I'm going to focus on some work that we've been doing looking at these early groups, particularly this transition from something that's getting close to a ton to something that's getting up to 5 or 6 tons. So this is going from something that's the size of a bison to the size of an elephant today, and looking at the ecology and habitat preferences of those particular groups. And so for my work, I focus on looking at isotopic chemistry in fossils. And in particular, this is one thing, if you have paleontologists coming through, particularly paleontologists that focus on mammals, they're always going to be talking about teeth, because 2 reasons. First, mammals have very complex dentitions, very complex teeth. So the teeth are usually very specific to a particular species or a particular group, so they're easy to identify. And then the other thing is that teeth preserve very well. They're the hardest elements in the body, in the skeleton, so they hold up really well as after burial. And that works great for me because enamel, which is the main mineral component within tooth material, the enamel is less prone to diagenetic alteration. So the isotopic chemistry of the original enamel in the tooth tends to persist for tens of millions, if not hundreds of millions of years. So we can use that as a reliable record of information. And that's kind of what I'm showing here. This is a XRD, or X-ray diffraction graphs. So it's basically zapping these teeth or bones or cementum with X-rays, and using the what gets reflected back or what gets lost as a way of gauging the mineralogy or the crystal structure. And so this is what modern bone, modern tooth enamel, dentin or cementum, their X-ray graphs will look something like this. And then after about 1.5 million years of fossilization, you can see that the enamel looks pretty similar to how it started, but the bone, cementum, dentin, all of these have shifted. So that suggests that bone and these other materials probably aren't good archives of this kind of information because they've been altered to some degree. Whereas enamel is pretty persistent, and so we can use that as a record. The other nice thing about enamel, and this is something probably most of you are aware of, is that enamel grows in layers. So if you have an animal like a horse today, which have these huge cheek teeth in their jaw, those cheek teeth can take a year or more to form. And that enamel crown is kind of like the basins where you have this really thick accumulation of material. You have a thick accumulation of enamel that can show you seasonal changes or at a finer scale than annual changes over the lifetime of the animals when the animal's living in its environment. So we can get long records of what this animal or this individual was doing based on sampling the isotopic composition across the tooth. So that's kind of what I'm going to be doing. Any of the isotopic data that I show you from here on out is primarily going to be focused on tooth enamel. And so to give you some little background on what we can do with enamel and bone, looking at the isotopic chemistry, there's two isotope systems that we work in preferentially. There's carbon isotopes, so different isotopes of the carbon. So this is carbon 12 and carbon 13. We're not working with carbon 14, which is radiocarbon, because we're looking at the stable isotopes, the ones that persist for a long time. And then oxygen isotopes, which I'll talk about a little bit later. The big thing about carbon isotopes is that, you might have heard with isotopic studies, you are what you eat. So the isotopic composition of the food you ingest gets incorporated into your tissues, and we can use it as a tracer. If that isotopic value of the food is unique, we can determine what your diet was. And the same thing we can do with animals in the past. We can distinguish animals that are eating a lot of plant material, different types of plant material, either browse up in trees or grasses on the ground, based on the differences in carbon isotope composition. So the reason we can do this is that don't look too deeply into this figure, but basically it all traces back to the atmosphere. So the primary source of carbon within the plants and the diets for these animals comes from the CO2 in the atmosphere, which then gets incorporated in plants with a certain discrimination depending on the type of photosynthesis that a particular plant uses. So trees, shrubs, cool weather grasses, so the grasses around here, primarily follow a method of photosynthesis we call C3 photosynthesis. And so they tend to have very light or very low carbon isotope values, around minus 26. So they're offset from atmospheric values about 20 per mil. Okay? In contrast, when you look at grasses that are growing in warm environments, tropical environments, those grasses tend to have, they fractionate to a lesser degree from the atmosphere. And so they have higher carbon isotope values, about minus 12. So because of this isotopic difference, we can distinguish an animal that's consuming plants in a forest or woodland environment from an animal that's eating grasses in a hot tropical environment. And there are isotopic differences. There's a big difference. So there's a small fractionation that occurs between the plant material and then what we get in the tooth enamel, and then we record that there. And that, so a C3 consumer, someone living in the woods, is going to have a value about minus 12, whereas something that's growing, eating grasses on the plains is going to have much higher value, about plus 2. So that's a big difference that we can look for in the fossil record. Just to show you quickly, this also can be a record from an abiotic perspective. So when we look at carbonate nodules that form in the soil carbonates also record the carbon isotope composition of the plants on the surface. So you can use that as a way of gauging, were there C3 plants dominant or C4 plants dominant, either from the tooth enamel of the consumers or the soil carbonates that are present in the sediments as well. So it's a really nice tracer that we can work with. And this just kind of illustrates this difference. These are carbon isotope values for C3 plants. This is carbon isotope values for C4 plants. Histogram showing the frequency, showing that there's no overlap in the distribution of those two groups. And then when we look at isotopic values from tooth enamel for different consumers, we find that there's a similar difference between those that are feeding mostly on C3 or C4 grass, have really high values, and then those are feeding in wooded environments or on the C3 plants have much lower values. And what's cool, and this is something we'll touch on a little bit later, is that when they sample tooth enamel from animals living in tropical rainforests, so really dense forests, their carbon isotope values are extremely low. So they're at almost minus 26 per mil. So they're easily identifiable in the fossil record as well. So you could not just tell that these animals were living in a forest, but you could determine if it's a tropical rainforest based on the carbon isotope values. Okay, so carbon can tell us something about diet, what things are eating. Oxygen, on the other hand, is a little more complicated because oxygen comes from multiple sources. Carbon is only coming from what you eat. We don't breathe in CO2, so we're not getting any of that from the atmosphere. But oxygen isotopes is going to be coming from the water you drink, the food you eat, the water that's in the food you eat, then also the air you breathe is also going to, because you take in oxygen. All of that gets mixed together, and then the isotopic composition that comes out is recorded in your tooth material. So that suggests that there could be some problems in trying to interpret this, but what we find is that for most animals, and I'll show you an illustration here, the biggest inputs of oxygen are primarily either food water or surface water, so the water you drink. So this is looking at the flux of oxygen that's going into an animal's body. And the three big pools that are shown here are atmospheric oxygen, which makes up about 25% of the oxygen that you take in, oxygen from the food that you eat, and primarily the water in the food that you eat, which can make up 45% of that, and then oxygen from the surface water that you ingest, which is about 30%. So the nice thing is that different mammals have different abundances or emphasize different fluxes within these three sources. So some animals have mostly drinking water recorded in their oxidized values, and some have mostly plant water. And when we look at the oxidized values for those guys, animals that drink mostly the oxidized isotopes, or get most of their oxidized isotopes from the water they drink, they don't show a big change in oxidized values when you compare it to water. So when you compare their oxidized values to dry conditions, so how much water is present in the environment, their oxidized values are pretty flat. They don't vary because they're reflecting that same source. For animals like this giraffe that are browsers, that are getting most of their water from the plant water that they ingest, they're showing a nice linear trend, whereas the water deficit, so the lack of water in the environment, or availability of water in the environment, means that their oxidized values elevate. And this is just because they're reflecting more of the plant water, and plants that are growing in really arid conditions, they evaporate a lot of water off out of the leaves. And so because of all that evaporation, you tend to evaporate the lighter isotope of oxygen. And so that leaves the water that remains in the plant really heavy. So it has a lot of the heavier isotope. And so animals that are ingesting a lot of plant water, their values are going to elevate as you get water-stressed conditions. So this is another level of information that we can pull out of these fossils to give us some indication about what the environment was like in the past. And then another direction you can go with this, and this is a study that I did back in 2008, is you can look at animals that spend a lot of time in the water. So things that are semi-aquatic, like hippos, they have a unique oxidized value relative to everybody else in the fauna as well. And it's basically because they're just acting as a data logger for the water that they're living in. Okay, so very little evaporation. And so they're showing generally lower values. So these are different parks in Africa where different species within the faunas have been sampled. And don't worry too much about what the different symbols in gray are, but just think of that as sort of the different fauna or different species in the fauna aside from hippos. When we look at the hippos, which are all in yellow, within any of those parks, at each park you get changes in the amplitude of the oxygen isotope values across the fauna, but hippos always have the lowest values. And that seems pretty consistent today. The cool thing is when we look in the fossil record, this is just taking those data and plotting the faunal values versus the hippo values. So we have fauna on the x-axis, hippos on the y-axis. The yellow diamonds here are the modern groups. Those are those yellow circles from the preceding graph. The red triangles, these are fossil hippos. So these are fossil hippos that are occurring in fossil faunas, and they show the same relationship, where there's this nice offset where they always have lower values. And that offset is typically about 3 per mil lower. So we see that both in the modern and the fossil. And the cool thing about that is that we can use that as a way of identifying animals that are spending a lot of time in the water. We can identify animals that are hippo-like in terms of their behavior and separate them out from the rest of the fauna in the fossil record. So that's a level of information that you often can't get just from looking at the shape of the fossils, because hippo fossils, these guys here, they aren't that drastically different from a lot of terrestrial fossils. There's some subtle changes that you can see. So if you didn't know that you were dealing with, or you didn't know anything about modern hippos, you probably would be hesitant to say that these things were aquatic or spending a lot of time in the water. But with the oxygen isotope values, we have a nice label that's independent of the morphology as a way of identifying how much time they're spending in the water. So using carbon and oxygen, this approach, these are the two tools that I'm going to be focusing on my talk and trying to better understand the faunas of the past. And not just who was there, but what were they doing, where were they living, maybe how they interacted with each other. And so for this time period, I've kind of focused in on that time period I described from 65 million years ago to about 35 million years ago. And this is just showing a blow up of that oxygen isotope curve. And I put this in here because one of the things that's often, I don't know if it's regularly discussed in talking about how mammals have evolved in North America over time. One of the things that's often forgotten is that there's a lot of immigration going on, a lot of movement of mammals between North America, Europe, and Asia. And so each of these warm events, so like this Paleocene and Eocene thermal maximum at about 56 million years ago, everything that's highlighted in pink, this is what we call a hyperthermal event, a short window when you've had really warm temperatures. And during each of those warming events, we have clusters of immigrants coming into North America. So initially, we have these Hyracotherium and Diacodexis. Anybody know who those guys are? They're kind of celebrities in the paleo world, that way. Hyracotherium was also called Eohippus at one time, the dawn horse. Yeah, so it's the earliest horse that we know in the fossil record, and it shows up in North America about 56 million years ago, right at the time that we have this big hyperthermal event. There's also Diacodexis, which is the first even-toed hoofed mammal that we find in the fossil record. So it's the ancestor to sheep, cattle, camels, hippos, antelope, deer, all those groups. So they show up right about this time. So this window here, the PETM, is a really important time period. And from a mammal age, we're talking about this transition from the Clark-Forkian to the Wasatchian. So this is when we get a shift in the types of mammals that are present, and that shift isn't just because things are going extinct and new stuff's evolving. It's also because new stuff's coming in to North America. So things that originated on other continents are coming in. And so we can look at that in a little more detail. So this is a stratigraphic range chart for different groups of mammals. Okay. The big thing that I want you guys to focus on, this red band here, this is the PETM. This is that 56 million year level, 56 million year event in the fossil record. And the thing that you see is that the earliest fossils of artiodactyls, perissodactyls, and primates, so monkeys, apes, they all show up in North America right at that event, so at 56 million years ago. And we call that the APP fauna, the artiodactyl, perissodactyl, primate fauna. And the interesting thing is that that fauna shows up everywhere that they show up. So in North America, Europe, Asia, at that time horizon, at 56 million years ago. We don't know where they come from yet. The general thought is that it might be India, because we know India is an island continent, and around 56 million years ago is when India may have started that collision with Asia. So the fauna that was on India could have gotten introduced to Asia and then spread outward. And the cool thing about these hot environments is that they allowed corridors in which the tropical environment spread northward. I mentioned they went all the way up to the Arctic Circle. So that was a consistent environment or habitat. So the mammals that are to the south can now move up to higher latitudes and take advantage of these land bridges. So like between Europe, North America, or between North America and Asia. And that's why you get this big diversification event during these warm events. So this PETM event is really important from a paleoecological perspective, because it's also the shift of going from what we call these archaic or sort of ancestral faunas with this guy here, this is Tilodon. This is another early mammal group that goes extinct during the Eocene. These were the dominant mammals present in North America until we go across this event, that PETM event. And this is when we get the modern faunas, so the ancestors of modern mammals, making their first appearance in the fossil record. The other cool thing about this event is that from an isotopic perspective, it's really unique. So this is some work that's been done by colleagues of mine, Gabe Bowen at the University of Utah, where they've been looking at cores of sediments from the Bighorn Basin in Wyoming. So these sediments were taken at Polecat Bench, which is a location near Powell, Wyoming. And these sediments, they subsampled, and they sampled the soil carbonates. So remember, those soil carbonates are recording the plants that are present on the surface and also the environmental composition. And just like the forams, the oxygen isotope values of those carbonates can tell you something about temperature. And so this record, when we look at the carbon isotope values of the carbonates, they start off pretty high, at around -9 per mil. And then as we go into the PETM, they drop dramatically. So depending on location, it can be anywhere from 3 to 6 per mil. So that's a big jump in isotopic values. And then they stay low for a while, and then they kind of return back to baseline values. And so the thought is that this is carbon, really light carbon, that's being introduced into the atmosphere. And so it's changing the isotopic composition of CO2, and this is a global effect. And so all the records across all the continents will show very similar isotopic excursions, which we've been able to find. So this is a nice marker for this event. So the shift in carbon isotope values tells us that you're in the PETM. So it's a very nice time horizon that we can work with. And then in addition, when you look at the oxygen isotopes, we can see that there's a big shift in temperature that accompanies it. So this is a really short amount of time, measured on thousands or tens of thousands of years. You get about a 5 to 8 degrees C temperature shift. So today we're talking about fossil fuels, which is a similar light carbon pool that's being put into the atmosphere. So this kind of has been done before in the past. And as I mentioned, there were a lot of extinctions that happened when that happened in the past. So, but with that projection, most of the, or the hope is that we're going to keep it to 2 degrees C. But that's going to have big climate and environmental impacts everywhere. This was 5 to 8 degrees C. So this was a really big shift in a very short window of time. So from an isotopic perspective, this is interesting in that it gives us an idea of, or a nice marker for a particular event, but it also gives us some information about the environmental conditions that the animals experienced over this time interval. So in looking at this, we can look at the mammal record, the fossils of mammals, and again, these are tooth specimens or fossil specimens that have been accumulating in these basins. So you get really high density of sampling across these basins. And so one of the earliest projects that came out of this, when this time horizon was identified, was that for some groups of mammals, and actually most groups of mammals, when you look at the size of the teeth, which is a proxy for the size of the animal, is that during this event, or shortly after this event, size dropped. And again, it's thought that it's this relationship between body size and temperature. When conditions get really, really warm, mammals get small. One thing that they found in looking at fossils in the tropic is that reptiles do the opposite. So reptiles get big. So it was not a good time to be a mammal in the tropics. You're getting small, the snakes are getting big. So this is kind of interesting from an ecological perspective in terms of how pervasive was this change in body size across different groups. And then it was, you can see it was pretty short-lived, just within that PETM event or shortly after it, and then right back to those original body sizes. When you look at across different groups of mammals, this is a study looking at several different species of mammals, both carnivores or faunivores, or animals with mixed diets, omnivores, versus plant eaters, the herbivores here. You can see that the majority of groups, when you look at the change in body mass as you go into the PETM, just about everything, either a few things stayed the same or everything got smaller. So there's a big drop in body size, and this is a 40 to 60 or even 70% shift in body size. So that's a dramatic drop in body size. And then after, as you go from PETM out of that event, you get this big push back to larger body sizes, up to 80 or 90% increase in body size out of that event. So this had a big impact on mammalian faunas. And so what I was curious about was looking at, when we look at the big mammals in this event, you'd expect them to be the ones that would be most strongly impacted by something like this. The big mammal for this time period, and this is this graph that I showed you earlier where we look at the maximum body size, was this guy, Coryphodon, which in the early Eocene and the middle Eocene, it was the largest mammal on the planet, and it was at about 700, late Paleocene, early Eocene, it was about 700 kilograms. So the size of a large steer, basically. That was the biggest mammal anywhere on the globe. And so what I was curious about is how did the ecology of this particular species change in response to this change in body size? Because we do know that if we look back, that its body size did decrease and then slowly increase back to what it was after the PETM. So it seems to be a slightly different pattern than what we see in some other groups of mammals where it's a very rapid shift and a rapid recovery. So being the big guy in the fauna, you know, a lot of the large mammals typically they're typically ecosystem architects, so they are engineers, so they're modifying the environment around them. So changes in the ecology of this guy, so this is Coryphodon, this is skeletal reconstruction of this guy. Sorry? Yeah, feel free if you have questions or comments, interject, that's fine. It's, you know, about the size of a steer, but based on the tooth material, this guy was really successful. You find it across the globe in Europe, Asia, North America, and part of its success was it was the first mammal with special teeth that were able to slice leaves. So it's one of these groups that was able to take advantage of a lot of plant material that was present on the landscape. Other animals kind of sampled plant material, but this was the first really big obligate herbivore within the environment. And most reconstructions and some of the work that we've done have suggested that in terms of habitat, it was probably most like, or habit, it was probably most like a hippo. So it had these large tusks, just like hippos do today, and then based on the deposits it's found on and some of the isotopic work that we've done, it's probably spent a lot of time in the water. So from an ecological perspective, for me, I'm very curious about how would this animal particularly respond to this event and how would its ecology change. So what we did was we looked at the oxygen isotope values, the carbon and the oxygen isotope values of these specimens from these different levels that have been sampled showing this body size change. And so with the carbon isotope values, the nice thing was we could see that we do see this drop in carbon isotope values. So the Coryphodon values are the yellow diamonds here. And you can see within the fauna, so the other symbols are different mammals from the same fauna or same location. There's this consistent pattern of Coryphodon having the lowest values within each of the faunas. But overall, that pattern doesn't shift over time. There's no big change. So ecologically, in terms of diet, they're doing the same thing. But this shift that we see here, this is the shift in the carbon isotope values of the atmosphere. And the nice thing is that that isotopic shift we can use to say these are definitely coming from that warm interval, that PETM event. Okay, so in terms of diet, nothing's really happening. But when we look at the oxygen isotopes, there are some differences that we see. So again, yellow diamonds are the Coryphodon values. Gray are other species from the same faunas. And you can see in the PETM, that separation between Coryphodon and these other groups is magnified or amplified, so it's even bigger. And then when we get in to the interval after the PETM, when we get this big drop in body size in Coryphodon, it's basically the same. You don't see any difference in those values. And then later on, when they get back to their large body size, that shift occurs again, so they're offset from everybody. And when we reinterpret this in light of that hippo difference, so this is taking the difference between the fauna and then the Coryphodon values. And remember, for hippos, we see about a -3 per mil difference, so 3 per mil lower values. That's represented by the shaded box here. For before the PETM, during the PETM, you can see that that offset is even more pronounced. These things are falling within that hippo field, so supporting this idea that these guys are spending a lot of time in the water. And it seems like during this warm interval, that behavior is being amplified. So they're spending probably even more time in the water because it's really hot. So if you're a big mammal, water is probably the best place to spend most of your day. But after that event, when Periphodon gets small, we see that that offset goes away. So they're basically the same as everybody else. So when they got small, they probably didn't have to worry about losing as much heat. And so they were able to be more terrestrial. So they weren't spending as much time in the water. So they were probably more pig-like than hippo-like during that interval. And then once they get back to their larger body size, they return back to that aquatic lifestyle. So this is an element of the ecology of these animals that we wouldn't have been able to identify if we didn't look at the isotopic chemistry of the teeth. The teeth themselves wasn't going to tell us this. So, yeah. So, oh, sorry, I'm going backwards actually. Okay, so that's sort of one big event in the early part of the Eocene. I want to give you a little bit of information about another hyperthermal event. This is going into the Eocene climatic optimum, so about 50 million years ago. And here's where we get different groups of hoofed mammals coming in, and then this one really weird group, which we call the Uintatheres. The large Uintatheres make their first appearance in North America during the early Eocene climatic optimum. So there are immigrants coming back in. There are earlier ancestral members of Uintatheres present in North America in the Paleocene and the early Eocene, but the big species of these guys don't appear until the early Eocene. Okay? And so I'm going to focus on this transition, this Wasachian-Bergerian transition that happened around 50 million years ago, and look at how Uintatheres responded to this other big warm event. And so to help you familiarize yourself, because most of you probably don't know what a Uintathere is, they're actually, if you ever got those little canisters of toy dinosaurs, there was often a Uintathere in it. They're these elephant-sized animals that have these lumpy spikes on the top of their head. So they had 3 rows of horns, one on the snout, one sort of in the middle, and then horns on the back of the skull. So they have this really strange appearance. And then besides having the horns on the skull, they also had tusks. So they had these big tusks that projected down. So they were pretty fearsome looking animals, but they're herbivores. They were plant eaters, just like elephants. And here's an actual skeleton of one of these guys from the Paris Museum, just showing the general body stance. So they look like an elephant, where the limbs are really more columnar. So they're kind of positioned right under the body because they're getting really heavy. So they're not running around a lot, they're kind of plodding along like an elephant. And as I mentioned, the big guys, these large guys up here, they make their first appearance as we get into this early Eocene climatic optimum. So this warm interval here that we see as this gentle hump in the oxygen isotope record. This is from the 4M record I showed you earlier. And then this is a parallel temperature record recovered from leaf material from Wyoming. So this is comparing global record of climate to local record of climate, showing both show this increase in temperature at this time. So there's a big warming in temperature that's going on. And across this interval is when we see this big shift in body size within Uintatheres, and in particular also in terms of their horn structure, so their cranial ornamentation on the skull. So this is the early guy. This is Prodinoceras, which is found from the Paleocene into the early Eocene, and it's, for the time period, it's actually a pretty big mammal at about 175 kilograms, so 300 or 400 pounds, so like a big pig, basically. But then over time, you get different genera like this Bathyopsis, then our guy Uintatherium, and then the last and most derived member of the Uintatheres is Eobacilius, that gets up to 4,500 kilograms. So think of that at about 5 tons body size. So these are the first mammals that get up to elephant size in the Eocene. And the cool thing about these guys is that when we look at, this is that same figure that I showed you earlier, looking at body size over time, maximal body size. Uintatheres were the first group in North America to get up to that 5-ton window. And then after that, this other group, these are brontotheres, the relatives of rhinos, they step in to fill that niche after these guys go extinct. Okay? So what's interesting is kind of comparing the two, because they're around the same body size and they're thought to be eating similar diets, but the morphology of these two groups are very different. So this group is closely related to living hoofed mammals. This group is something totally different. It's a completely extinct group. And when you look at the dentition and the horn structure, so the cranial ornamentation is similar. You know, these guys do have bony structures that make up horns on the head. These guys have tusks. These guys don't. But the big difference between them is in their teeth. So with Uintatheres, if you look at for the size of the skull, the cheek teeth are actually really small. So a brontothere of about the same mass or body size as this Uintathere has much bigger teeth. And so it's thought that they're doing a lot more oral processing, like they're really pulverizing the plant material in their mouth before they swallow it. Whereas these guys are doing very limited modification or mastication or chewing of the plant material before they swallow it down. And it's thought that with these big brontotheres, if you look at their cheek teeth, if you've ever looked at those, or if you have one of those vegetable slicers or choppers, you know, with the little button that you press down, the shape is very similar to the teeth of these guys, where you have that W-shaped, and they're doing the exact same thing. They're slicing the vegetation, getting very small particles for swallowing, so it's easier for digestion. The teeth here are much simpler than what we see with these guys here. Besides being bigger, they're also simpler. And so when I showed you that graph earlier where we're looking at body size using tooth size as a proxy for body size, this is the trend in body size or tooth size for Uintatheres or this group Dinosaurata. And it's not a big change in tooth size over time. With brontotheres, as they get bigger, their teeth get really big too. So if you just had teeth, you would come up with very different estimates of body size comparing these two groups. So it's kind of problematic, and it suggests that their dentition is probably, and their diet was probably very different between the two groups. So what we've done is, last graph, so this is sort of a fun aside. So you probably don't see too many images of skeletons from the rear of fossil mammals. But this came out of a conversation I had with Kirk Johnson, who was at the Denver Museum of Natural History. He's now at the Smithsonian. And he told me this story about when they had done a life-size reconstruction of a Uintathere for a museum in Utah. I think it's in Vernal, Utah. And they put it all together, you know, matched it up, the proportions of the skeleton. And they were going to move it into this room. And so the front half of the animal went through just fine, and then the back half got stuck. and so he explained it that from in comparison with modern species today, Uintatheres are like rhinos from the front and elephants from the back. And so they had to shave off parts of the hips in order to get it through the doorway and then fix it later once they got it through. But so I got curious about this, looking at these reconstructions of skeletons, and yeah, it's kind of true. When you look at the pelvis of, this is a woolly rhinoceros, this is a Uintathere here, and then this is an elephant. Both the elephant and the Uintathere have these really broad pelvic bones in the back that are probably helping to support big guts. So these guys, the reason their teeth are so small is that they're not doing a lot of the work. They're letting their gut bacteria doing the work. And so that's why they're really, if you look at them from above, they have this very pear shape to the body, where it's narrow at the front and wide at the back. And so they have very different physiology than what we see in rhinos or in brontotheres, so that other group that's living at the same time. So this informs us that there's probably going to be big differences when we look at these guys isotopically as well. And so what we've done is look at material that we have in the collections at Wyoming. So there's several localities, and these are localities from the Washakie Basin, so in sort of the south central portion of Wyoming. So one of those big basins that's really accumulating a lot of material. And the nice thing is that we have material from Paleocene into the Eocene. So we got a good representation of Uintatheres across that interval from these different sites. In addition, oh, sorry. We also went back out in the field. This is a field season 2006, 2007. This is looking at the Washakie Basin, Adobe Town member, Washakie Formation. We're collecting Uintathere fossils from this locality. So there were 3 different specimens that we found from this one site that we could include in our collection. So different students that were out there working with us collecting the fossils. I think this is Laura Vietti, who came and gave a talk a while ago from our department. She was part of that group back when she was a undergrad at the University of Wyoming. And so from those fossils, the ones that we have in the collections and then the ones that we accumulated later at these different field trips, we're looking at the tooth enamel and using it as a proxy for the diet and environmental information. In addition, we also sampled some of the bone material. So I mentioned that that alters fairly quickly. So we could use that as a way of gauging how well the enamel is preserved. So we should see a big difference between the two. They shouldn't overlap if the enamel is preserved and the bone has been altered. So I'm going to show you a series of graphs that are just looking at carbon-oxygen space. So oxygen values are going to be plotted on the x-axis, carbon values on the y-axis. And I'm going to go through these kind of quickly. But we start in the early Bergerian, so this is early Eocene going into that early Eocene climate optimum event. And when we look at enamel isotope values for Brontothera from those deposits and an early Uintathere from that deposit, their isotopic values are not that different. They're pretty similar. And in particular, their carbon isotope values are almost the same. So diet-wise, they're probably doing very similar things. And then the nice thing is that the enamel values are very different from the bone values for those deposits. So it's suggesting that the enamel's much better preserved and showing and recording different information than the bones are. If we move forward in time, going in late Bergerian, this is another specimen. This is Uintatherium. And these are some of the specimens that we collected in that field season. Uintatherium has pretty low carbon isotope values, very consistent. And again, compared to the bone values from that same deposit, no overlap, so good preservation there. And when we compare it with Brontotheres and rhinos from that same time interval or slightly later, the Brontotheres and the rhinos all plot with higher carbon isotope values now. So there seems to be a separation between these two groups. And this is when we get that 5-ton body size between Brontotheres and Uintatheres. So when they get big, there seems to be this divergence in what they're feeding on. And that holds up even further in time when we go into the late Uintan. So the last genus of Uintathere that we find, this is Tetheopsis, it has much lower carbon isotope values. And these all seem to kind of stay the same, whereas the Brontotheres and the rhinos are moving towards higher carbon isotope values. So they're changing their diet over time, whereas the Uintatheres are staying the same. And what we think is happening is when we compare all these groups together, we get this nice separation between the later Brontotheres and rhinos and these Uintatheres or Dinosaurata species. So these guys are basically conforming and consistent in what they're doing over time. These guys are adjusting or adapting what they're doing over time. And they're isotopically distinct from one another. So what we think is happening is probably that as climate is shifting and floras are shifting, because we're going from this warm interval, things are starting to cool, these guys are the first guys that are going to go extinct because they're stuck eating one particular diet. We don't know exactly what that is, but one particular diet item. Whereas these guys are shifting their dietary preferences as the climate and the flora shift. And that's what we see is these guys go out at about 40 million years ago. These guys make it to the end of the Eocene until we get that big climate change when Antarctica starts to accumulate ice. So trying to tease out what these values actually mean, separating deep forest from woodlands. There's a possibility that some of these Uintathere samples have carbon values that are low enough that they could be living in really closed or almost tropical rainforest conditions, but it's not many. But in general, the big difference is just the separation between Brontotheres and rhinos. And so in conclusion, we can look at the enamel carbon isotope values and we see that they're significantly lower than other big herbivores from the same location once they get to that big body size, and that their enamel values didn't shift dramatically over time. So it suggests that within the middle Eocene, so around 50 to 40 million years ago, they kept things the same. And it's probably that restricted diet or habitat preferences that they're not adapting to change, is probably what facilitated their extinction or led to their extinction at the end of the Middle Eocene. Oops. So in conclusion overall, I just want to reiterate that the fossil record in Wyoming is amazing, and it gives us an incredible window into how faunas and environments have shifted over time. We wouldn't know how warm and how tropical environments were in the past if we didn't have the fossils as a record of that. And then one of the big stories that we see in the Eocene particularly is that a lot of these really warm intervals are associated with immigration, with the movement of new species coming in from the other continents as these warm temperatures allow things to move over a broader range across the globe. And then the nice thing is with the geochemistry is that it gives us a different level of information from the fossils that we wouldn't have had if we just looked at the shape of the fossils. But looking at their composition can tell us differences of things living in the water versus living on land. And that's a topic that I'll go into a little further tomorrow. And when I talk about the early evolution of whales and marine mammals. And then it also can give us some information about more closed environments versus more open environments as you move from woodlands to grasslands. So with that, I will stop there and take any questions. Yes?
The Paleocene and Eocene thermal maximum was precisely the time when Greenland and Norway were drifting apart, which would have limited difference. I'm wondering if there's any clear evidence whether these new species that suddenly showed up were the result of very rapid evolution because of the hot temperatures and changes in vegetation, or were different?
That's a very good question, and that had always been debated because we don't really know, for most groups, we can't really tell when this APP fauna, the artiodactyls, perissodactyls, and primates, which continent they show up first, where do they start. However, there was a study using this geochemical signature of the PETM that was able to identify the origin for at least one genus of mammal, and it's a little early primate relative. And based on its position within the sediments at different locations in Asia, Europe, and North America, they could track it moving from Asia, Europe, to North America, showing that it moved in that direction. And there was consistent morphological change as it moved, that you could identify the early form from the later form. So with that insight, at least for that one species, they were able to do what you were asking. For other groups, it's still problematic. They just sort of appear at roughly the same time. But if other paleontologists might look at it at the same level of detail that they did for this one primate species, they might be able to get a little more information about that.
But the ones that suddenly appeared are the ones we're descended from.
Are the ones that, sorry?
The ones that suddenly appeared are the ones that we're descended from.
Yes, our modern fauna. Yeah, so the primates, that's the first origin of primates at that time. Yeah.
What about cats? Were those ones that came later in the Eocene, or were they around before?
That's a good question. So carnivores in general, so including cats and dogs and bears and weasels, all those groups, they really just sort of appear in the early Eocene, and they're sort of background players. They're sort of the small omnivorous, maybe carnivorous groups. So they were all sort of weasel-like or ferret-like at that time. And then there were other groups of mammals, these archaic groups or earlier groups, that were the dominant meat eaters during that interval. And once those groups go extinct, then you get carnivores, I'm sorry, to speak correctly from a paleontological standpoint, we call them carnivorans, because they're part of the group Carnivora, to differentiate them from carnivore in the general sense of anything that eats meat. So the carnivorans really take off in sort of the middle Eocene into the late Eocene, and then as these other groups go extinct. But cats themselves, they were sort of important more as you go into the late Eocene and the Oligocene. Cats were important carnivores in North America. And then we have a period which we call the cat gap, when we don't have when we don't have any true cats in North America. And during that interval of time, dogs, so relatives of dogs today, became more cat-like and became what we call hyper carnivores, where they just ate meat. Their teeth were really specialized for eating meat. And so they kind of filled that void until cats come back from Europe and Asia. And so Europe and Asia seem to be like the zone where a lot of these mammal groups are originating from. And it's probably, Asia's a larger landmass, traveling a larger latitudinal range, so you can get greater diversification that way. So I hope that answered your question. Oh, yes.
So do you have any concerns about, you're talking about carbon-13 concentration in mammal, and that often is due to diet, you're saying, but due to deposition while they're forming the enamel on teeth, right?
Yes,
So
yes.
Is there a concern that is like you wouldn't catch a shift in diet post-development?
Yes. Yeah. Once the tooth has stopped forming, you're not going to see it. With living mammals, the nice thing we have is that the crown forms over a pretty distinct window of time of about a year or two, depending on the species. But the root can grow throughout the rest of the animal's life. So the root can give you 30, 40, 50 years of information for an individual. And some animals have these really big tusks, like elephants or rhinos, or any of these groups that have the big tusks. Those tusks are generally ever growing as well, and so you can get a lot of information out of that. Unfortunately, from our perspective, from a paleontological perspective, the dentin that makes up the root alters fairly quickly. So you lose a lot of that information, and you can only rely on the enamel crown.
And also kind of on that, if you're seeing a shift in body size and also a shift in diet towards grasslands, are you also seeing a thickening of the enamel to deal with the silica from the grass? Or?
Yeah, you often see it. So often the crown will increase in height. So they're investing more in the tooth so that it'll last longer with that really abrasive diet. And then also the shape of the tooth will change based on the function. So I'm showing that a lot of these guys that, like the brontotheres that have that chopping style of tooth, those guys try to keep that edge sharp, and they keep very sort of a high profile shape to it. Whereas grazers, things that are eating stuff that's really abrasive, they tend to have more of a washboard pattern because everything gets worn down and they have more of a flat surface over time. So you can see as they shift their diet, the tooth shape also shifts as well, and then the wear features on the teeth shift as well too. Sure. Yes.
What kind of primates were here during the PETM? By here I mean North America.
Okay, so I'm a little out of my league because I'm not a primate specialist, but they're very early primates. So we do know that they're arboreal, so they're spending a lot of time in the trees, and so I can refer you to some papers that will have more information on those groups. But generally they're small, and they're thought to be ancestral to all later primates at this time. And then most of them are thought to be more insectivorous early on. Some of them have really large eyes, so they might have been nocturnal. And then later groups, you start getting things that are able to eat more fruit and material, and that's all based on the tooth shape that we know. And that's about as far as I'm going to go into that, because I could probably get myself into trouble if I try to go any further. So.
You won't get in trouble here.
Right, but there's that video that's going on.
Mark, I have a question. The PETM, Cretaceous and Eocene thermal maximum, I know that there's a lot of discussion about that, but when people think about how fast it might have occurred, what is the fastest that people think it could have happened?
Well, so that record I showed you from the Bighorn Basin where they had the drill core, so prior to that work, people have been focusing on outcrops and collecting soil nodules from outcrops and measuring isotopic change. And that's where it was first really identified in terrestrial records, was from the Bighorn Basin from outcrop exposures. The issue you run into with outcrops is that outcrop exposure means that everything's been weathered to a certain degree. That's how you get the exposure. And so you don't get as detailed a record out of that. So once they did the core, what they found was that there's actually 2 spikes in carbon isotope values. So there's a little shift first to lighter values, and that's thought to have happened maybe 2,000 years, like really, really rapid from a geological perspective. And then the big one that followed after that, about that same amount of time, roughly. There's still debate over how much time is actually represented, but from a geological perspective, it's pretty fast. So that shows that there were 2 pools of light carbon that were available and ready to be released at that time.
And those might have been?
What's that?
And those might have been?
Early on, it was thought that it might be methane clathrates.
Yeah.
So these are marine, where you get some methane in deep sediments, or sorry, in deep ocean, where it's really cold. They tend to form these sort of stable, almost solid structures. And then once temperatures get warm enough or the pressure decreases, they release. And so you get this big belch of methane into the atmosphere, which has a really light carbon isotopic value. And so you wouldn't need a lot of methane to cause that big shift. There's been other talk of volcanoes or volcanic eruptions that went through peat deposits or a lot of organic deposits. And there is evidence of large volcanic events around this time. So I don't think it's really been resolved, but I think most people still sort of lean towards the methane clathrates as the primary source. Yeah?
Can I ask you a more fundamental question on the migration of the species between various areas of the globe?
Mm-hmm.
What is the mechanism? Land bridge, ice bridge, being
Yeah.
stuck on a landmass as it moves, or all of the above?
All the above. Over time, it's all the above.
Yeah.
But for this interval, it's primarily land bridges that opened up. And by land bridges, they're close proximity. So the continents, there's not a big stretch of water that they have to cross. And they're probably established before the migration events actually occur, the movements actually occur. But it's with this climate change where you have these tropical climates that then move northward that create these extensive forest conditions that now create a forest path over that environment, that create the habitat that's ideal for these animals to move.
So it might not be a geological movement of the land, but instead of deforestation and aggregation of soil, etc.
Yep.
Build the bridge.
Exactly. So they just have the conditions were right to allow these groups to the south to move up north and then cross over. Any other questions?
So, following up on that, if it is a warm period, there's theoretically more water than ice,
Yes.
which
Yeah.
would mean that areas would be flooded versus more land appear.
Mm-hmm.
So that doesn't compute for me.
Yeah. So part of this, kind of getting back to your comment earlier, even though we do have Greenland and Europe and separating around this time, it's a slower separation. So they're actually closer at that period than they are today. And so that's probably what's allowing these movements to actually occur for some of these groups. You're right that there is definitely more water at this time, and with warmer temperatures and thermal expansion, the water is even going to be, further or further elevated. So it just had to be that the proximity was right. I'm not really sure what sort of land bridge was present at that time, but whatever it was, the forest habitat was able to move far enough north that a lot of these southern or tropical species were then able to cross over whatever land bridge was present at that time. And it could be something as simple as, like island hopping. If the distance between the land masses is not too great, you can get random dispersal events through this. But the fact that we have artiodactyls, perissodactyls, primates all showing up, all making this leap at the same time, suggests that land bridge was pretty substantial. It wasn't just a big gap. There was something that was facilitating that passage. Any other questions? Yeah.
So if you have some of these larger mammals with the very jagged teeth for cutting and emulsifying the leaves, why do they have tusks?
Why they have?
What is the purpose of the tusk?
Oh, that's a really good question. Yeah. So most mammals that have these large tusks that we can't really identify like a dietary function associated with them, because some animals that do use the tusks for feeding, you'll see where the tusks actually cross against one another, and then where or occlude, sorry, that's the word I'm looking for, occlude. But with these guys, the tusks are separate. They don't really interact with many of the other teeth. And so we think it's more for display. So there's been some work. We don't have a lot of fossils of this particular group, the Uintatheres, but the ones that we do suggest that there might be sexual dimorphism, where the females have a slightly different skull structure, the horns aren't as pronounced, the tusks aren't as large. They still have tusks, but they're just not as large. And then they're more enhanced than the males. And so it's probably used for display.
We have time for one more question.
Yeah.
So APP is primate. The other two, what type of animals are those? I think you said that I didn't log in.
The A is artiodactyls. So those are even-toed hoof mammals like camels, sheep, goats, deer. The other P is perissodactyls. And those are the odd-toed hoof mammals. So like rhinos, tapirs, horses. Those are the other two groups.
Yeah, so before we break up, two things. One, if you want to review some of what Mark has said, our videographers.
He hasn't published.
Oh, okay.
His information yet.
You're going to have to wait
So
6 months or 18 months?
About something. Hopefully 6 months. Hopefully, yeah.
And then you'll be able to see it. But on behalf of the geologists at Jackson Hole, Mark, we want to thank you for absolutely incredible presentation.
Thank you very much.
There'll be more tomorrow. Please join me.